have clarified what the optimization problem is, now we will learn two solutions of unconstrained optimization one by one. The first solution is the gradient descent method. Gradient descent method is a first-order iterative optimization algorithm to finding a local minimum of the objective function. Ideally, we assume the objective function is convex. Therefore, we can get the minimal easily. So, what is the convex function? Why it is useful? We use the following graph to explain. On the left, we can distinguish a local minimal and a global minimal. From the graph in the middle, we can see it is easy to find the global minimal whenever the point starts. However, from the right-hand graph, we can see the ups and downs with many local minimal over here and there. And we are not sure which local minima is the global minima. It depends on where the point starts, and those are what we call the convex and non-convex function, which are shown in the three-dimensional graph. The middle is the convex, which follows this formula. Ideally, we assume our objective function is convex, then it could be easy to find the minima. Because the advantage of a convex optimization is that all local minima are also global minima. To begin with, the sample size should be determined since it can vary from a handful of parameters to many thousands. For simplicity, we will consider the example in two-dimensional, which we can visualize in the cost function services to explain how the gradient descent works. First, we have the original blue point, and then with the guidance of the search direction, we can go downstairs. And the step size will determine how long it will take to find the minima. In this way, we could find the minima to solve the optimization problem. If the problem or data size is in n dimension, and we assume the objective function is convex, and we need to confirm the direction pk and step size alpha k. pk is specified by this negative gradient, and alpha k is also called the learning rate, which is a positive scalar. We can define the learning rate alpha k by ourselves in most experiments. The stopping criteria are the gradient of the point is 0 or close to 0. It would be clear to explain the gradient descent in a visualization way. Starting at one point, we take our first step along the direction of negative gradient. Each step size is updated by the learning rate. We can set the value by ourselves. Next, we recalculate the negative gradient, passing in the coordinates of our new point, and take another step in the direction it specifies. We continue this process iteratively until we get the bottom of the function, or to a point where we can no longer move downwards, a local minima, in which the gradient of the minima is 0 or close to 0. The right-hand figure is the control plot of the function with the steps of the gradient methods. The gradient is everywhere perpendicular to the control lines. After each line is minimized, the new gradient is orthogonal to the previous direction. Therefore, the iteration trace tend to be the zigzag down to the valley.